Today we are getting into 8.3, which is vectors in three-dimensional space. And I love getting into this stuff because once we go into three dimensions, once you start doing things in three dimensions, the amount of real world applications that show up is just insane, right? Because we live in a three-dimensional world. So learning math in three dimensions um, has a lot of benefits, obviously. Of course, math in two dimensions also has probably more benefits than we would like to think, or that you guys would like to think or can think of. But right, I think three dimensions is a lot more obvious of how it directly pertains to us, and especially vectors, right? Anything that has an angle or moves at a velocity or has acceleration in three-dimensional space can be described with a vector, right? So wide ranging. But for the think slash home, I have if X and Y make a two-dimensional plane, what do you think would be a good letter to add to denote a third dimension? Anyone, probably the easiest little check for participation you guys could ever get. Yeah, I need to move the talking thing. Who first said Z? Was it Mason? Okay, good job, Mason, and and everyone else that answered. That was a pretty good one, right? And that's exactly what we're going to do. We're going to add Z on there. So we've always worked in two dimensions in math, and you've become very familiar with the XY plane. But we can add a third dimension, which, as I said, gives us many more real world applications. And we can just add Z on top of X and Y to help us denote a third dimension. However, it is kind of weird to us when we first start graphing it. So the x-axis will be coming like in and out of the page, and the y-axis will be left and right, which we're not used to, and z will be up and down. And so for this first example, I have locate the point 4, -3, or -4, 3, 2. And I'm just going to kind of, hopefully, this is really important to maybe write down how we graph these things. So I'm going to do my best on this tablet, but essentially how the axes go is, I don't know if I should do it in lines or if I should sketch it so that you can see how to sketch it. I'll try both. So we have up and down. This is how I do it. We have up and down and left and right. I basically make an X and Y plane like we always have had. And then I kind of shoot this out this way and this way. And hopefully we can kind of, my tablet is messing up. Hopefully we can kind of see how that looks like three dimensions, right? We have our, it's not X and Y like we used to have, but now it's X, Y, and Z. This is the X coming, you can think of it as coming out of the page and then going into the page almost. This will be our positive Y, right? So negative Y is this way, negative X is into the page, right? And then this will be our Z, where up is positive and down is negative. And so I would definitely take a moment to sketch this. And I think I actually did a pretty good job sketching it. It's one of those things I remember. I feel like I wasn't introduced to a three-dimensional graph until I was in Calc 3 in college. Maybe it was in pre-calc when I was here and I just wasn't paying attention or something. But my God, I remember in Calc 3 in college, I was looking at this, and for some reason, my brain was just not clicking of how the three dimensions looked. But hopefully, you can kind of, as soon as you understand that maybe this X is coming out of the page at you, and the Y is left and right, and Z is up and down, hopefully, we can kind of see how this is like a corner of a box here, right? And then we can maybe sort of see the third dimension. And fair warning to you guys, I suck at drawing things in the third dimension. But what we're supposed to do when they say locate this point, we're supposed to graph it using this like box method where, okay, and again, this is what's called an ordered triplet. You know, we're used to X and Y, but now we have X, Y, Z. Right, so X is -4. This is the negative X direction, so I'm going to go 1, 2, 3, 4, right? And then we can kind of think of, or let's plot another one. Then y is 3. This is the positive y direction. 1, 2, 3. And we can maybe make a dotted line there between x and y, right? That's where they would meet up. And now z is positive 2, so up 1, 2. And we could think of z as creating a box with y. And really, it's also hard. Hold on. It's also getting pretty scrunched. I'm just going to do this way. So x was negative 1, 2, 3, 4. Y was 3. Z was 2. And we kind of do this thing where we go there, but then we need to go up 2 to the z, which is going to be like up here, right? And we do this weird, like, you essentially make a box. It's kind of hard to do, right? We can maybe kind of see the box forming now. It's so cramped there, but I think you guys would get the point as long as you can understand. So essentially, you're supposed to kind of get this box looking thing, except it's supposed to all be dotted. And then this point here is where this would be. I know it's pretty cramped and tough to see right there, but hopefully that helps, right? If we connect the x and y's and then the x and y's and z's, we make this box in the corner here is the point we have. And hopefully that can sort of help us visualize where the point is at in space. It's a lot easier if you have a program or something and you can like actually like twirl it and look around at it. But yeah, that's how we kind of graph, right, with this box method. And terrible artist, so it doesn't look that great. But hopefully we can all. I think I did a pretty good job on the axis coming out of the page, y left and right, z up and down, and making that axis. So hopefully that is helpful to us. Now, this should look very familiar. The magnitude of a vector x, y, z is the square root of x squared plus y squared plus z squared. Basically the Pythagorean theorem, except we're tacking on z squared in there, right? And then if you go from one point to another point, remember when we did it in 2 dimensions, right? We had x1, y1. And if we went to a point x2, y2, we did the change in x, right? This would be the change in x, or x2 minus x1. This would be the change in y, or y2 minus y1, right? And then Pythagorean theorem, x2 minus x1 squared plus y2 minus y1 squared got us the magnitude here. Now that we're in 3 dimensions, it's pretty much the same idea, except now we have that z squared, or z2 minus z1 tacked onto there. Colton said something happened to his screen. Is everyone else's screen okay? I suppose the better question is anyone else's screen not okay? I'm going to take that as a no. So Colton, you might just want to like back out and then come back or something. All right. And I can go back to this if we need it. Again, you don't need to write down all of this. I would write that the magnitude is that, or if you go from one point to another, it's this, right? It's really just an extension of what we did in 2 dimensions. So does anyone need a little more time on this slide? All right. I'll give it a little while longer. Good, Colton. Correct. Okay. Do we need any more time on this slide? I think we're probably good now. If not, let me know. Don't mind hanging back. Okay. So write the ordered pair triple, or the ordered triple. Sorry, I said pair because I'm so used to saying ordered pair. Ordered triple that represents the vector from x to y of these 2 points. Again, it wants us to write the vector, so we should have these little fancy symbols. And I just like to think, okay, the change from x to y, the change in the x's is -1. The change in the y's is -2, and the change in the z's is +4, right? Or that's really if we do, x2 minus x1, y2 minus y1, or minus a negative is plus z2 minus z1. And that gets us -1, -2, 4. Right, and it does matter that we're going x to y. You can't go backwards, right? Because it wants this vector xy. So, and again, I think it's just so much easier to think. Change from the change in the x's is -1. The change in the y's is -2, and the change in z's is 4. From here to here, how much have you changed? That's it for that one. Anyone need more time there? You should use, if you're writing it, you should use these pointy parentheses, the ones that are a little more straight up. If you're writing it, right? Because if you do like this, like I'll know what you're talking about, of course, but you don't want to be writing less than and greater than signs if you can avoid it. And the other lesson, it's a pain. It's such a pain to write these in equation editor, these pointy ones, but I did it in this lesson to kind of throw the idea home. Like this it takes so long in equation editor. But if you happen to type something, right, then I would accept it because you guys probably don't know much about equation editor, and there's no way I would expect that. But if you're just freehanding it, I would make them the vector symbols so that we're being accurate. No. Those, because parentheses they denote like points, right? And the whole point of vectors is that we need to know that vectors are just something different, and so they're denoted differently. Otherwise, then you're like, it's like saying the wrong thing in math. I don't know if that's the best way to word that. It's like you using words in math that like you would be saying something you're not intentionally saying. I think you know what I'm saying. So again, kind of a similar start problem to that lady on the stretcher. Like, why are we working with a honeybee? But a three-dimensional vector can be used for anything, right? You could pretend that this is the International Space Station flying in orbit if you would like. That seems a lot more realistic to me than determining the flight of a honeybee. But here we are talking about the flight of a honeybee. So let's just do this example, realizing that while you guys aren't going to find the flight of a honeybee probably ever, there's a million other applications that happen when you turn things into 3D vectors, right? Anything flying around, anything moving around in space, which is literally everything, pretty much, right? This stuff is useful. So suppose the flight of a honeybee passed through points at 033, 504, in which unit, in which, oh, I should say, in which a unit represents a meter. What is the magnitude of the displacement the bee experienced in traveling between these 2 points? So it wants the vector, right? The length of it, the magnitude. And so I would like to write it instead of, so here, from point to point, you can use this formula, but instead of doing that, I think going and using this is so much easier, but then you need to know what the vector is. But I think it's really easy to determine what the vector is, right? From this point to this point, 0 to 5, we've gone 5. 3 to 0, we've gone -3. And from 3 to 4, we've gone 1. Right? So we've gone like 5 units kind of at us out of the page, -3 units to the left in the y direction, and 1 unit up in the z direction. Right? So, right, if it was like kind of coming at us and but to the left because the -3 in the y direction and up 1 in the z, it's kind of hard to freehand. I'm not even gonna try it because you need to draw the whole thing. But this is x, y, and z, the change in all of them, and so the displacement is basically the Pythagorean theorem, except it's 5 squared plus -3 squared, right? That would be the x and y. And now we just add the 1 squared on top of it. So we get 25 plus 9 plus 1, 35, which just has to say the square root of 35. So that is the total displacement. All right, because if you try and break 35 down, done. Can't even break it down anymore. So nothing comes out of that square root. So for this one, for the magnitude, I found the vector, right? And the vector is easy to find from 2 points, right? It's just the change in x, the change in y, and the change in z, right? How much have you moved in the x direction? How much have you moved in the y direction? How much have you moved in the z direction? And now this is basically just an extended Pythagorean theorem. Pretty easy. I think we might be able to finish so that tomorrow we can just spend the class time to do our 3 problems or even maybe move forward a little bit. Does anyone need more time on this one? Okay. So find 3p minus 2q if p is this and q is that. Well, 3 times p is going to be 3 times 304 and minus 2 times q is 2, 1, -1. So then we get 9, 0, 12 minus 4, 2, -2. 9 minus 4 is 5. 0 minus 2 is -2. 12 minus -2 is going to be 14. Right? Adding and subtracting vectors just like we did in 2 dimensions, same in 3 dimensions. You just have to match up the z's like you did the x's and y's. Not a big deal. Right? I think we're all probably pretty comfortable with that. And I will give it a second in case anyone was writing down that problem. So we'll get out of here. We only have a couple extra minutes, but the last part is quick. You guys could have probably honestly done one of these without an example anyway. Pretty intuitive. All right. We go to this last one. And then remember how we said we did these unit things where we made I an X direction unit and J a Y direction unit. We're gonna do that same thing, except we're gonna add a third one, and I, J, K, we're gonna make Z equal to a unit vector of K. So write AB as the sum of unit vectors for A is this and B is this. Again, I'm going to write it as a vector. The change in X from 5 to -1 is -6. The change in Y from 10 to 4 is also -6. And the change from -3 to -2 is +1. Right? So that's the vector. Right? And so now we just write -6. Oops, not J. X goes with the I's. Minus 6J. Plus 1, which we don't need to write, plus 1, or not Z, K. That's all this one wants. Just wants this vector written in unit vectors. Right? So instead of in these brackets, it wants it in I's and J's and K's.